Dear students, today's topic is an n-bit binary adder. The topic code is ELEC-DIGIE-S8. We have seen in the last topic with a single bit binary adders, half adder, and it is a full adder. When we were discussing that, the 1-bit binary adders can be constructed from basic logic gates. But what if we wanted to add together two n-bit numbers? Then n number of 1-bit full adders need to be connected or cascaded together to produce what is known as ripple carry adder or cascaded adder. A ripple carry adder is simply n 1-bit full adders cascaded together with each full adder representing a single weighted column in a long binary addition. It is called a ripple carry adder. Now let's go to the details are given. Let's go to the practical things, understanding the things how this is made. Now this is a n means the n number of numbers you want to add. But in this case we take the, instead of n is equal to 4-bit, okay, n bit means you can have the binary number with a n number of bits, okay, so one odd-end and another add-end, so we want to add them. But here we take, let's say n is equal to 4, let's say 4-bit ripple carry adder we would like to make. So that means we will be having first 4-bit numbers of A0 to A3. Okay, we will be doing the example in the next coming at the end of the slide. And then we have B0 to B3. These are the 4 bits. Suppose we want to add them together. So A0 to A3, these are the 4 bits, and again B0 to B3, this is the second number. This is the first number, which is the 4-bit number, and this is the second number. We would like to add them together, second 4-bit number. So what we do now, we take the full adders and connect them in cascaded form such that the carry out is fed into the carry in, similarly of the one, and similar carry out of the next to the carry in of the next, and so on and so forth, and then lastly we get the carry out. So we can use here the half adder as well, okay, but you can use it, but with a 0 input value or the binary bit, it is considered as a half adder, but full adder can also be used, no problem with that. So what we get, it gives rise to a sum bit S0, S1, S2, S3, a carry bit C0, A0, B0, they will add it together, there will be a sum and a carry. They will added together, it will give rise a sum and a carry, which is C1. Again A2, P2, this is now the 3rd bit, first bit, second bit, 3rd bit. That is the, in the second, in that 0th order we have started, so that is the A2, B2 is, it will give rise S2 sum and the carry. And similarly A3, B3, when you add it together, 2 bits, they can have 0 and 1, 0 and 1 values, and S3, and the next is carried to the carry is C out. So one main disadvantage of cascading together 1-bit binary adder to add large numbers, one bit binary number. So this was the large number is that the inputs A and B change the sum, and its output will not be valid until any carry input has rippled through every full adder in the chain, because the most significant bit of the sum has to wait for the changes from the carry input of the least significant or the less significant bit. Consequently, there will be a finite delay before the output of the adder responds to any change in the inputs, resulting in an accumulated delay. So the now let's go to the this was the adder. Read out that that's a practical example. Now the IC 7483 or 74LS83 logic, this is a TTL IC. This is a typical example of the 4-bit adders. It consists of, it has again 14 pins. You can see the 4 pins to the input first binary number, then again 4 pins for the second binary number, 4 pins for the sums S0 to S3, 1 pin for the C in and 1 pin for the C out. So that's how the it is. The IC has the 4-bit full adder circuitry pin connection. Now let's see the binary subtractor. There are two cases, two scenarios, or two methods which we use. This is the first we would like to see, that we call the half subtractor and a half. The two half subtractors together make a binary subtractor, full binary subtractor. Let's see, we will discuss that later. So binary subtractor, the binary subtractor is another type of combinational arithmetic circuit that produces an output which is the subtraction of two binary numbers. So as their name implies, a binary subtractor is a decision making circuit that subtracts two binary numbers from each other, for example x to y, to find the resulting difference between the two numbers. Unlike binary adder, which produces sum and a carry bit when two binary numbers are added together, the binary subtractor produces a difference d by using a borrow bit b from the previous column. Then obviously operation of subtraction is the opposite of that of the addition. That is, it is a special case. You can also say the negative or the complement of that number. If you take the second number, complement it of the number which is going to be subtracted. We learned from our maths now lesson at school that the minus sign is used for subtraction calculation, and when one number is subtracted from another, a borrow is required if the subtrahend is greater than the minuend. Consider the simply is greater than the minuend. Consider the simple subtraction of the two. Ordinary means the decimal number system, base 10 numbers below. We have these two numbers 123, 78. We subtract them, the difference is 45. This is called the subtrahend, this is called the minuend. This one is the minuend, this is the subtrahend. So when the minuend is higher than the subtrahend, so it's no problem with that. 45, the difference is 45. We don't, in this case obviously we do take the borrow. The 3 is smaller than 8, so we take 10 borrow from that is the base, one complete base from the next column. It will become 13. 13 minus 8 is 5, and then similarly we do the subtraction. We left here is the 11, and 11 minus 7 is 4. We cannot directly subtract 8 from 3, as in the first column we have as 8 is greater than the 3, so we have to borrow a complete base which is 10, the base number from the next column, and add it to the minuend. So that is, I have explained. Let's move on. So the binary subtraction can take many forms, but the rules for the subtraction are the same whichever process you use. A binary notation only has 2 digits, subtracting a 0 from a 0. Here details are given. 0 minus 0 is 0, 1 minus 0 is 1, 1 minus 1 is 0, but 0 minus 1 means the difference is 1, borrow is 1 in this case. In this case differences are given very straightforward, no problem with that. But if this minuend is less than the subtrahend, then we have to take borrow from the next, whichever the column is there. So now two input exclusive OR gate is here. Let's go to directly to the binary subtractor. In binary subtractor, two these again will be used components, which is the exclusive OR gate and the NOT gate at the input of the first X, and ended with the second as a B is equal to, the output is equal to borrow, as a borrow X complement dot Y. So borrow will be described by this gate. Now let's see, first this is the half subtractor. Half subtractor is a logical circuit that performs subtraction operation on two binary digits. The half subtractor produces a sum and a borrow bit for the next stage. So we have the two inputs X and Y, a difference and a borrow output. There will be a borrow output, so X minus Y difference and a borrow out. So this is the typical symbol the inside the subtractor, half subtractor, which has the exclusive OR gate and AND gate, but with the one of the X is being complemented, or the NOT gate is introduced to make it as a borrow. So in this case, if you remember the binary adder, this was as a described as a sum, but in this case it is now borrow. Let's see now. 0 minus 0 is 0. 0 minus 0 minus 0 is 0. 1 minus 0 is again the difference is 1, and the borrow is 0. Okay, in this case the 0 minus 0 is 0, the borrow is 0. Now in this case 0 minus 1, because now 0 is less than the 1, we are subtracting from the higher number, so difference is 1, the borrow is 1. We have to take borrow from it, so it will generate a borrow in this case, so borrow is 1. Similarly 1 minus 1, which is the difference, is 0 and borrow is 0 in this case. So if you put this in this logical expression, you will get the same results. Here we have the difference is X exclusive RY, X exclusive RY, borrow is not X, mean X is noted, and Y, X bar Y, or X complemented Y. Okay, so a full binary subtractor we have got now. A full binary subtractor has the two inputs and one binary input, two XY input and one borrow input, and one borrow output and a difference. So X minus Y will be having its capability to also the borrow in. Okay, in the half subtractor that doesn't have that capability. So let's see now the logic circuit diagram is again the two half subtractors are cascaded together, two inputs X and Y, one the borrow input which is fed to the second input of the second half subtractor, and the output difference is fed to the first input of the second half subtractor. This is the output, which is the difference D, and this is the borrow out, which is the B in complement into the X exclusive or Y. This is X exclusive or Y, again X exclusive or B in. So this X exclusive or Y, this and these two is B in. These two make here the exclusive or operation, while in this case we have the from here the internal the same borrow circuit, which is this half subtractor makes that the output circuitry. We'll see that in detail, the truth table as well. This is now the circuitry. Here we can see that the borrow out is made from the following circuitries. Again, if you can see that in the first half, this is the first half subtractor, this is the second half subtractor. So the two inputs and one borrow in input, which is fed to the directly the second of that one, and then obviously these AND gates are there. The X first has to be gated again, it has been means the complemented again and fed here. Then the product of these two will be X exclusive R complement, because the NOT gate is complementing into the B in. So these two are again in OR gate, they are added together, the output coming from here, which is X bar into Y, X bar Y, so that will be the B out bar out. So this is a truth table. You can just see that the three inputs gave rise to the difference and the borrow out. So in this case, we can see here we have the last this expression. In this case, we can borrow out in three cases we got. When the X is 0, Y is 1, then the 0 minus 1, which is the again 0 is smaller number, 1 is higher number, so we have the difference is 1, borrow out is 1. And the another case which we have is the binary in we have got here. So this is again when we have the in this case difference is 1 and borrow out is 1, and the other two are the Y is 1 and B in, borrow in is 1. Then we have the in this case we have the sum is 0, the difference is 0, but the borrow out is 1. In this case we have the difference is 1 but borrow out is 1. So this is in last we have all of these are 1, then difference is 1 and borrow out is 1. So this logical operation, you can just simply put them and make the truth table, and you will come up with the same these results. These are actually obtained, difference is obtained, this difference is obtained from this whole logical operations. Okay, the expression we have already given, and borrow out is obtained from this expression. These two we'll in a moment we'll here the difference is obtained from this whole expression. This is expressed the X or Y, this is X exclusive R Y, D is can be simplified over here. The exclusive R Y, Y or exclusive R B in is equal to exclusive R Y exclusive R B in. So D is given by this relation. So this D difference bit can be expressed. Let me show if I have calculated that one somewhere. D difference. Okay, here is the calculation I have calculated for you. You can do it as well, and you will get this expression, okay, which is given in that X bar Y bar B in plus X Y B in plus X bar Y B in plus X Y bar B in bar. Okay, so if you simplify X exclusive R for the difference, we have exclusive R Y exclusive R B in, then exclusive R Y is given by X bar Y plus X Y bar, and this is as it is we are putting here. Then we have the in this case, okay, now what we have to do now, this is now considered a single unit, like it's a whole one unit and a second unit. So we will apply the same exclusive R gate on it. Okay, exclusive R gate means this is X and this is Y, so X bar into Y, then X into Y bar. Okay, just like we have to again. So do it, all these calculations, it is there for you, and you will ultimately find this expression which we have in the equation as described over here. Let me show the main equation here. So that main expression is calculated by simplifying this particular this term, this whole x exclusive ry exclusive r b in. So that's the we have got. Now let's see an n bit binary subtractor. That is the typical. This is 2's complement. The second method, I'm going to do the example as well, one each in the addition and the subtraction. The 2's complement means the first we apply first complement, second complement we did it. So 2's complement, what we do, this is the first number, the second number you want to subtract. The number which you want to subtract, you put complements, that is the NOT gates over there, 2's complements, and then you add them. It's a 4-bit binary adder and also be used as a subtractor. Okay, so that is the second method which I was mentioning, and in this book, in this particular the topic also been discussed. So let me now give you the examples. Let's now we would like to first addition, do the 2 binary numbers you would like to add. This will give you the comprehension of the this topic. That we have 2 numbers. This is the first number, this is the second 4-bit, and this is the first 4-bit number, this is second, which is A0 to A3, B0 to B3. This is A0, A1, A2, A3, B0, B1, B2, B3. Let's say this number is 1101, which is in decimal number system is 13, and this is in by the decimal number system is 14. So when we add these two, we get the 27. So 1 plus 0 is 1, 1 plus 0 is 1, 1 plus 1 is 0, which is 1 carry, 1 plus 1 is 1 0, and 1 0 plus 1, which is a carry 1 1 1. This is the result. So if you convert them, you will get obviously the 27 to the base 10, but this is the binary number. So we would like to add these 2 numbers. These are a 4-bit ripple carry adder. So here we have 4 full adders, 2 inputs each. Okay, A0, B0, A1, B1, A2, B2, A3, B3. So let's say we starting from the least significant to the most significant, which is 1, again 1 0 1 1. So 1 0 1 1 to all A's. Then we have to the B's 0 1 1 1. We go starting from the least significant to 0 1 1 1. So now here we have, now what we do, what it does, the full adder, it will add this 1 plus 0 is 1, sum is 1, the carry is 0, 0 plus 1 is 1, carry is 0, so nothing to add. So 0 plus 1 is 1, sum is 1, carry is 0, 0 is again carried. 1 plus 1 means the sum is 0, carry is 1, you don't have any carry. Now here we have 1 plus 1 is 1 0, 1 0 plus 1 is 1 1. So 1 is sum and 1 is carry. Carry is over here. So this will make the number 1 1 0 1 1 to the base 2 as we get the result. This is how a binary adder 4-bit 4-bit binary numbers are added together. Now let's see the next. Now the subtractor, binary subtractor. This is now to 1's complement when the A is greater than B. So what we do, this is again, now this time 13 is the number and this is 11 is the number, 13 minus 11. So this is 1 1 0 1 1 0 1 1. Obviously this number is the menu end is higher than the subtrahend. So we are going to subtract, we should get 2, answer it should be 2. So here normal subtraction, we 1 minus 1 is 0, 0 minus 1 we take 1 is 1 0 carry, we take 1, 1 0 minus 1 is 1, and we have got 0 and 0. So 1 0 is the answer, which is in the base 2. In the base 2 is 1 0, and then the decimal number system it is 2. So now what we have to do, this is now the typical binary subtractor. Now this is now that we will be ones complement. What we do, we will add these two numbers, but before that, in 2's complement or 1's complement, what we do, the second number is complemented and added together. This number 1 0 1 1, we take the complements of them, but now the polarity, this will be changed from minus to plus, because we have complemented all the b's, the second number which are going to be subtracted. So it will give rise now the complement of this 1 0 1 1 is 0 1 0 0, because this is 0, this is 1, this is 0 0. So what we get now is we add these together. 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0, carry is 1, 1 plus 0 is 1, and 1 plus the carry, if you add, is 1 0. Now in this what we do in this process, we add this carry bit. This is now the carry bit is taken to the input and added to the first number, which is 1 plus 1, which is 1 0. So that number, the carry bit, last carry bit, is fed into the input. The first number is added, which is 1 plus 1 is 1 0, which is the answer. Now let's apply that to the this is the 2's complement method. We have 1's complement, we have complemented the 1's complement, means we have complemented this and added the carry bit to the first one. This is the procedure and the rule for that. So we have again 4 full adders. Now b's have to be, the actual b's are b0, b1, b2, b bits are the second, the number which is r is given here as a 1 1 0 1. Actual number is 1 0 1 1. So least significant to most significant, we move on. So what we do, we introduce at each b a NOT gate which will complement this 1 into 0 1 to 0 0 to 1 1 to 0. Just we have in this case 1 0 0. This is the 1 0 0. 0 is before, that is insignificant, it's not significant. So now these output of these each complemented or NOT gate are added with the A0s, A0 A1 A's. So this is now 1 plus 0 is sum is 1, carry is 0, 0 plus 0 is sum is 0, carry is 0, 1 plus 1 is 1 0, which is sum is 0 and carry is 1, 1 is carried over here, 1 plus 1, 1 plus 0 is 1, 1 plus 1 is 1 0, 0 is here and carry is over here. Now this carry is fed back and added here to the first bit. So it is 1 plus 1, which is 1 0, which is the result. So this was the case when A was greater than B. Now if the A is less than B, then 2's complement method will be used. Double complement, we will in the beginning we will take the complement, again at the end we take the complement. So again we take now this time 11, which is the in the menu end, and the subtrahend is 13. We are subtracting the larger number from the smaller number. So answer will be minus 1 0, which is the minus 2 in case of base 10. So what we do, again we complement the subtrahend, we again the same way which we did in the last time, but sign now we change it from negative to positive, so it will be 0 0 1 0. Now this one, remember, this is now the other number. So when this is added together, what we get is the 1 plus 0 is 1, so 1 plus 1 is 0 1, 1 is carried, 1 here, 1 plus 0 is 1. So what we have, 0 is the carry, so carry is carried on and it doesn't make any difference. Then what we do, the second, we apply the complement. This was the first complement, and the inverting again we will invert the first complement or this one. After the second complement is made, the result of these two, that is the 1 complement, 0 complement, 1 complement. What we get, 1 complement is 0, 0 complement is 1, and 0 0 we get the complements. We put now a negative sign with it, sign bit, we call it 0 is now negative sign bit, so we put a minus sign with it. 1 0 is the answer. So here is now the again the same of the 4 bit, the full adders. We would like to add two numbers the same way we did for the other one. Now again each NOT gate at the B. Now B is a higher number, remember, so we have put over there, and the taking the complement of each, so 1 into 1 0 0 1 1 0 1 0. A's are again 1 0 1 1, so they are added together in the same way. We get the same which we have done the addition over there. The 1 plus 0 is 1, carry is the 0, because sum is 0, sum is 1, carry is 0. 1 plus 1 is the sum is 0, carry is 1. 0 plus 0 is 0, 0 plus 1 is 1, 1 sum is 1, carry is 0. So in this case 1 plus 0 is 1 and carry is 0, so it is 1, carry is 0. So 0 is carried all the way. So what we get now, we take now the second complement with the negative sign bit. So second complement, we get the complement of this whole number, whatever the sum we have got. One complement, that is the we are complemented over here. The here result is 0 1 0 0, and putting a negative sign for the inverting that sum, the second complement. That means the second complement guarantees or shows that it is a negative number, so you have to put it when you reach to the second complement, then you have to put that the negative number with the result. So minus 1 0 is the result. Okay, dear students, with this we reach to the end of the topic. We will meet again inshallah with a new topic. Thank you.